Hello, good afternoon, good morning, good evening, and everyone. Welcome today to Elias Talk. And today we are thrilled to have Dr. Lahtinen with us today. So Dr. Lahtinen is a chief scientist, a co-founder of Quanscient, and a distinguished expert at the intersection in computational physics, mathematics, and then quantum technologies with over 15 years of experience. So his academic journey includes the appointment at Aalto University and others, and his research field is into quantum science, quantum technology. So without much talk, I would like us introduce Dr. Lahtinen so that he takes us through to this section. So yeah, welcome, Doc, for this session. So this is ELAIS 2024, and these are your students.
Thank you very much for the introduction, and thank you very much for inviting me to give a talk in this prestigious course that you are hosting. So, yeah, indeed. The title of my talk today is Quantum Native Multiphysics Simulations. As mentioned, I'm the chief scientist and co-founder of Quanscient. We are a Finland-based startup doing multiphysics simulations with cloud computing and quantum computing. In particular today, I will be talking mostly about the quantum algorithms research that we do for this type of multiphysics simulations at our Quanscient Quantum Labs. But I will also very briefly introduce Quanscient in general in the beginning. So first, I will give a very brief overview of Quanscient, and then I will dive into quantum algorithms for multiphysics, kind of presenting the overview of the different methodologies that can be used, and then diving deeper into what we call quantum native multiphysics algorithms that we are developing at Quanscient. And finally, concluding. So Quanscient is still a relatively young startup company. So we were only founded in 2021, but of course we are basing our technologies on decades of research. So in that sense, the technologies have been developed much longer time. But already in 3 years, we've grown to 35 employees. We've raised roughly $10 million in funding, and we are headquartered in Tampere, Finland, a small technology hub in Finland. And even though we are based in Finland, we have people working all over the world. So we have several people in Germany, in UK, some people in the US, and also one person in Japan. And altogether 14 different nationalities. We are growing a very vast fundamental quantum software patent portfolio with our quantum algorithms research. But at the same time, we already have a product out there, and we have customers who are running thousands of simulations weekly on our platform. So yeah, the product that we have out there currently is called Quanscient also. And that's still purely cloud-based multiphysics simulations tool. And we have the idea to eventually integrate the quantum research that we are doing, the quantum algorithms that we are developing as a part of this Quanscient also tool. But currently, the product that's out there, that's still purely classical cloud-based multiphysics simulations tool. However, we do have very fundamental quantum algorithms that we will eventually integrate. But already with the current tool, we've demonstrated more than 1,000 times speedups to increase the complexity of the simulations and decrease the runtime really from days to coffee breaks compared to some of the competitor software. So this we do with our very efficient domain decomposition methods. Because we are fully cloud-based, so the computational capacity is not really a problem. So the user just accesses the tool with his laptop, and the user doesn't have to have their own hardware except for the laptop or a mobile phone even. Basically, just an internet connection to access the tool, and then all the computations will be done on the cloud. And what this really enables you to do is automate your workflows. So with our APIs, for example, you can really integrate these solvers as a direct integrated part of your engineering workflows, for example. If you want to do some optimization or machine learning training, things like this, it's very easy to generate a lot of data with this kind of tool, a lot of simulations data. And as I mentioned, in the end, we really want to make the impossible simulations possible. So even though we can already achieve these more than 1,000 times speedups compared to some competitors, the idea is to have these exponential speedups with quantum advantage from the quantum algorithms for the users eventually as well. And when I say multiphysics simulations, I mean mainly simulations of classical physics. So things like computational fluid dynamics, computational electromagnetics, heat transfer, and combinations of these kind of things. So without further ado, let's go to the quantum computing part. So let's dive a bit deeper into what is kind of the status of quantum computing for these kind of multiphysics simulations. But first, let's think like what sort of a toolbox do we have in general in use currently with quantum computers? So as you are probably already aware of through this course or otherwise, in quantum algorithms, we really want to use quantum phenomena, superposition and entanglement of qubits, and so on, to solve problems. And we present these quantum algorithms using these quantum circuits where you have quantum gates operating on qubits. And however, the current state of quantum computing is such that all the current devices are still quite immature. So we call this noisy intermediate scale quantum era, and these devices are noisy intermediate scale quantum devices, often referred to as this NISQ era devices. So they are very noisy and unreliable in this sense. So you really need tailoring for different computers. You really need specialized optimization of your algorithms to be able to run something meaningful on today's devices. And what that means is that really every gate of these quantum circuits will matter. So you really want to optimize these quantum circuits to the max. What you also really need is these noise mitigation techniques, error mitigation techniques, error suppression techniques, to really get the most out of the current quantum computers. And what we do at Quanscient, because we want to develop these algorithms and we don't want to be so much focused then on the noise mitigation or error mitigation, so we have partnered with many of the leading companies in this error mitigation business. So we don't have to worry about that so much as ourselves, but that's a really important part of running anything meaningful on the current devices, really. And the device agnosticity is quite hard because when you compile this abstract circuit model of your algorithm into actual hardware, that can still really make or break the algorithm because, for example, the qubit topology, the connectivity of the qubits varies from device to device. And that can lead to many, many more gates than you originally intended. And you really have to kind of tailor in this sense for all the different qubit topologies of these different devices. So being device agnostic is quite hard. And what's kind of important to notice is that these quantum processing units, quantum computers, they can provide advantage as local computing units for specialized tasks. But really, you need this classical computing, HPC, whatever, to really orchestrate the whole thing. So there is really no quantum computing without classical computing per se. You always need the classical computers to orchestrate the quantum computer. So that's kind of the toolbox that we have in use today. Of course, in the future, we are looking at error-corrected fault-tolerant quantum computers, which will be much more universal in this sense. But to do something meaningful on today's device, you really have to take all these kind of shortcomings into account. Okay, looking at multiphysics simulations. So again, simulations of things like computational fluid dynamics and combining this with, say, heat transfer and so on. So this is what I mean with multiphysics. If you look at kind of the standard quantum algorithms for multiphysics, you can kind of divide these in two types of algorithms. So the first on the left is what we call kind of the linear algebra-based algorithms. So you have your favorite discretization method of the partial differential equations that you are solving. So finite difference method, finite element method, finite volume method, so forth. And what you always end up doing in those methods eventually is solving linear systems of equations to solve these PDEs then on a macroscopic scale. And then there are these different types of quantum linear solvers, such as the HHL algorithm or variational algorithm for linear systems and things like this, that you can then utilize to solve the linear systems that result from these discretization methods, like the finite element method. And that's one way. The other way is what we call the quantum native way. And this is what we are looking at Quanscient as well. And examples of this are, for example, the quantum lattice Boltzmann methods and quantum lattice gas automata type of methods. And next, I will kind of go through both of these sides of the coin and then show in the end some proof of concept simulations as well. So let's first look at the quantum linear solvers. So the most well-known quantum linear solver is the HHL algorithm, quite obviously. And it's as I said, a very famous algorithm that actually allows you to solve linear systems of equations in logarithmic time. And that's the quantum advantage right there. So if you think of best classical algorithms for sparse matrices for solving the matrix equation AX equals B, the best classical algorithms for sparse matrices do that in time n log n. Now the quantum version of AX equals B would be to construct quantum state X that fulfills A operator operating on the state X equals quantum state B. And what the inventors of this HHL algorithm showed that if we have a Hermitian A, we can actually construct the related Hamiltonian and find the eigenvectors and eigenvalues of A using the so-called quantum phase estimation algorithm. And basically this will allow you to then to construct this state X in logarithmic time. And then in the end, you can extract some expectation value of that X. So some global properties of the solution, basically. And this is of course, this is great quantum advantage right there. But some of the issues related to this HHL algorithm are that if you have an arbitrary input matrix A, so if you don't really have any structure in A that you can take advantage of, there is no known efficient algorithm for encoding that arbitrary input matrix A and vector B into the quantum computer. So you can actually lose the quantum advantage already at that point. Now, if they have some structure, then there might be some tricks you can do, and you might not lose the quantum advantage in the encoding stage. But if it's arbitrary, then it's tricky. And the complexity, the logarithmic complexity, it's not quite just log n. It also depends quadratically on the condition number of the matrix, and it's also proportional to solution accuracy. So the more iterations you sort of need to get to a better accuracy solution. And as I said, you cannot really extract efficiently the solution vector x, but you can only extract some global properties, so some expectation value. So what that would mean in terms of multiphysics is obviously something like a integral of the solution. And that can be, of course, very interesting. So thinking of, say, computational electromagnetics, that could be, for example, capacitance or inductance or energy of the system. And these can be very interesting engineering properties for sure. So it's not a showstopper, but it's something to take into account. But especially for NISQ era devices, the HHL algorithm produces too deep circuits currently. So the noise will take over quite soon, and you cannot really solve very big systems with the current devices with HHL. Now, for fault-tolerant quantum computing, I'm sure that HHL will be a great tool in the future. There have been some further developments of the HHL algorithm, such as extensions to dense matrices, not only dealing with sparse matrices. There's been some improvements on the precision dependence. Also some hybrid formulations, so that you use some classical a priori information, for example. But still, really solving problems of very significant size accurately has remained elusive with HHL to date. But a very potential algorithm for future. Another option is this so-called variational quantum linear solver that has been especially tailored for NISQ devices. And the variational quantum linear solver is really basically a classical optimization procedure that optimizes the parameters of the quantum circuit. So this way you can really have quite short quantum circuit itself, but you have the expense of the classical optimization loop there. It has potential for speed up for solving linear systems of equations compared to classical solvers. But it's obviously less efficient than HHL in terms of the complexity. And also it's kind of heuristic algorithm in some sense, so it's kind of hard to say what is the exact complexity there. And you have again the same problem of efficient input of arbitrary matrices and arbitrary vectors. You have the issue of coming up with an efficient ansatz. So you might easily end up in these barren plateaus. And so given some ansatz, you quite easily end up in these barren plateaus, and you might get kind of stuck in a saddle point in the optimization. But again, a promising algorithm, but it still has some issues to be resolved. So because of these linear system solvers for quantum computers are not quite there yet in terms of being able to solve something meaningful on near-term quantum computers, what we are doing at Quanscient Quantum Labs is more this quantum native approach. And in particular there, kind of the flagship methods that we have been developing are quantum lattice Boltzmann and quantum lattice gas automata type of methods. And when I say quantum native, what I mean with that is that there is kind of a direct analogy between the evolution of the quantum system, the QPU, and the evolution of the physical problem that we are solving. And what is very nice with these lattice-based methods, lattice Boltzmann and lattice gas automata, is that with each qubit that we add, we can double always the size of the grid that we are modeling. So the problem size grows exponentially with linear increase in qubits. However, with many problems, we can show that actually the required computational operations, the required number of quantum gates, grows only logarithmically with the problem size. So in this sense, we have exponential speedup compared to classical lattice Boltzmann and classical lattice gas automata. So that's very nice. In quantum lattice Boltzmann, we are not solving linear systems of equations directly. We are not solving even the partial differential equations directly on the macroscopic scale. Rather, on this lattice, we are evolving mesoscopic probability distributions of particles. And from this evolution, from these collision and propagation processes that we use to evolve these probability density distributions on this lattice, we then, on the macroscopic scale, can eventually generate the solutions of different partial differential equations. And as I will show, we have already demonstrated accurate results in 1D and 2D, also on real hardware. And we've also worked on 3D simulations. And then the quantum lattice gas automata, that's very much related to the quantum lattice Boltzmann. So there we are not really evolving probability density distributions of particles, but actually we have individual particles that we are evolving, again, using these collision and propagation processes. And there the nice thing is that from this very simple particle collision, we can actually generate on the macroscopic scale very complex nonlinear phenomena. And there's a level of statistical averaging involved to these lattice gas automata type of simulation. And that really accounts to some noise resilience because that can mitigate some of the noise coming from the real devices of today. So lattice Boltzmann method, classically, it's a well-known method for solving especially computational fluid dynamics problems, CFD problems, but also it can solve many different types of partial differential equations, in fact. So it's been used for acoustics, for elastodynamics, for electromagnetics, and so on. But it originates from computational fluid dynamics, and that's kind of the main use case that it's used for usually classically, as well as the main use case that we have been using it in the quantum version as well. And as I said, we are not really talking about a particle method here, so we're not tracking individual particles, nor we are solving, for example, the Navier-Stokes equations on the macroscopic scale. So we are not, generating some matrices from the Navier-Stokes equations directly and then solving them, but rather we are dealing with these mesoscopic distribution functions of particles. And now these mesoscopic probability density distributions, these probabilities, they can be directly encoded into the amplitudes of the qubits. So using amplitude encoding, we can actually directly encode these probability densities into the amplitudes of the qubits. And then evolving again using these collision and propagation processes, these probability density distributions on these lattices, we then actually generate on the macroscopic scale eventually the solution of the PDE. And yeah, as I mentioned, in terms of quantum lattice Boltzmann, one of the most appealing properties is this analogy between these lattice Boltzmann method probability distributions and then the quantum qubit amplitudes and the measurements that we get. So the probabilities that we get from the measurement eventually actually directly correspond to these probability distributions of the lattice Boltzmann method on the lattice. And we can show that this collision and propagation step can be efficiently solved on quantum computers. So in fact, the propagation step is basically just a quantum walk. and the collision step. Now that depends from problem to problem because that's where you actually encode the interactions of the problem. But for many problems, that can be very efficiently solved as well. And as I mentioned, the problem of encoding an arbitrary matrix, for example, for these HHL type of solvers can be a difficult problem. But for this lattice-Boltzmann method type of simulations in CFD, for example, you can actually often start the simulation by just evolving from the zero velocity field. So you don't really have to encode a lot as the initial state. So that's also kind of an appealing property. And in terms of extracting the results, so we again have the possibility of extracting, for example, some integral of the solution, like we would have in the linear system type of solution as well. But we can also, for example, zoom in to some particular part of the modeling domain, and actually from those probability density distributions that we directly get from the measurements, we can actually also have a look at the solution itself quite easily in this lattice-Boltzmann method. And as I said, lattice gas automaton it resembles a lot the lattice-Boltzmann method, and in fact, lattice-Boltzmann method originally was developed from lattice gas automata. So lattice gas automata was quite quickly abandoned, in fact, in classical research because lattice-Boltzmann method took its place. But now with quantum computing, lattice gas automata have some really appealing properties, and it's kind of gaining more traction again in the quantum research community. So with lattice gas automata, as I said, we're not dealing with these probability density distributions, but rather we have purely Boolean lattice sites. So you either have a particle or you don't have a particle, basically. So you're dealing with zeros and ones in this sense. And again, you have the same type of propagation and collision steps as in the lattice-Boltzmann. And here in the figure, you can see a 2D lattice gas automata simulation actually being run. But why we want to do quantum lattice gas automata then is that really these collision operators are extremely simple. So with lattice-Boltzmann method, you would have to, if you have a nonlinear problem, you have to linearize somehow the collision operator for the quantum computer. With lattice gas automata, the collisions are always linear. They're super simple and linear, while still generating on the macroscopic scale, they generate actually nonlinear phenomena. So for example, we can show that we can generate the Navier-Stokes equations from this simple particle lattice gas automata that have linear and simple collisions. So the nonlinearities are resolved naturally in that sense. So you really have this nice unitary linear collision from the get-go. And as I said, the statistical ensemble average that you do, so you really run a lot of these lattice gas automaton simulations, and then you average out to get the macroscopic behavior. So that can actually mitigate some of the noise that comes from the error-prone quantum devices of today. But okay, what can we do today with these kind of methods? So let's look at some concrete use cases of quantum simulation. So I emphasize here that these are still, very much proofs of concept. So obviously we are not solving something super huge and super meaningful, and we have not yet obviously shown quantum advantage, except on the algorithmic scale, of course. So the algorithms themselves have quantum advantage, but because the devices are still small, noisy, intermediate scale quantum devices, we cannot yet solve huge problems, but we can already show that this is possible. And with the promise of quantum computers developing as they are developing at the pace which they are, we expect to see quantum advantage with these methods in medium term. So here first, a very simple proof of concept with quantum lattice gas automaton. So this is a very simple 1D HPP quantum lattice gas automaton. And what you're simulating here basically is just this wave of concentration starting from the middle and then going towards the walls and then reflecting again back from the walls. So very simple simulation in that sense, but it's a proof of concept that this can be done. And what's interesting here though is that you can see these different noise levels here. And for example, the mid-level noise is the noise that comes from today's device, Quantinuum H2 device. So the single qubit error rates, the 2-qubit error rates, and the readout error rates are from Quantinuum's H2 device. And you can see that the noiseless and so we compare this simulation that has the real noise with completely noiseless simulation of the lattice gas automaton. And you see that we actually get really good results even after several tens of time steps. So really already with today's devices, lattice gas automata can be simulated. So that's a really nice and encouraging result in that sense. Then going to lattice Boltzmann methods. So here is again a quite simple benchmark of motion of 1D and 2D Gaussian hills simulated using the quantum lattice Boltzmann method. So on the upper left corner, you see the 1D advection diffusion equation being solved, and the solid lines are the analytical solution, and the dots are the solution from the quantum lattice Boltzmann method. So it's nicely validated that we get the same results. And on the right, you see the same thing, but in 2 dimensions, compared again with analytical results and classical results. And on the bottom left, you see kind of the result that you get from the real device. So these are the probability density distributions that I mentioned. And from these probabilities, just by summing up these probabilities for different lattices, you actually get the macroscopic values that actually represent the solution of the partial differential equation. So the thing you see on the bottom left is actually coming from the Quantinuum's H1 real device hardware. This is something that we did together with VTT Technical Research Center of Finland. So this is kind of a very rudimentary model of aerosols or some pollution spreading in a room, for example. And these are basically, these represent the same problem, but with just different input parameters and a little bit different simulation grid. But what we did was we solved this again with our quantum lattice Boltzmann method. And what VTT did was they have their own classical lattice Boltzmann solver. So they validated that we get exactly the same results. Now these are coming from a simulator, so not from a real device, but this could be run on a real device as well. And to show that more complex problems than advection diffusion equation can be solved as well. So this is the standard benchmark of a cavity flow, so lid-driven cavity flow, where you have this moving wall boundary condition at one wall, and then you will start to see these vortices to form in the fluid. And again, this was solved with our quantum lattice Boltzmann method and validated against similar classical solver. But okay, these were still kind of toy problems, if you will. So to show that these algorithms already can do more complex things with more complex boundary conditions, we've also solved this Naka airfoil problem. So you have an airfoil and you solve the airflow around the airfoil and the temperature transport with it. So you have an inlet on the left and an outlet on the right, and then you have the airfoil there in the middle. And so basically what we're doing here with the lattice Boltzmann method is that we are solving the Navier-Stokes equations using the stream vorticity formulation, which is basically coupling two lattice-Boltzmann equations together. And then we couple a third lattice-Boltzmann equation for the temperature solution to that. So we are solving three coupled lattice-Boltzmann equations with this quantum lattice-Boltzmann method here. And this kind of brings another level of quantum advantage into play here. So not only we have the advantage of exponentially large grids with the number of qubits, but also as we couple these different lattice-Boltzmann equations together for solving these multiphysics problems, we can do this in superposition. So actually we don't have to add computational resources while we solve more and more lattice-Boltzmann equations in superposition. So that's another nice feature of the lattice-Boltzmann method or the quantum lattice-Boltzmann method, that you can solve many equations in superposition. And again, this has been validated fully against the classical simulation. So quite complex problems are already possible with quantum algorithms, and this is coming from a simulator, but we are working on the first proofs of concept for this airfoil problem as well on real devices. So very briefly on what is on our roadmap in terms of quantum simulations at Quanscient. So as you've seen, we've already have quite a lot of actually concrete evidence that these quantum native macroscale physics simulations can be done already on today's NISQ devices, as well as quantum simulators, obviously. And what we've been now hardly, or not hardly, but hard working on is that we are extending, or we have been extending the 2D simulations, as you saw, also on real devices, but also we have done our first 3D simulations. Not yet on real devices, but that's kind of the next big holy grail that we're looking at. But we've also been extending to more different types of physics here. So as I mentioned, the lattice-Boltzmann method is a very general method for solving different types of PDEs. So actually what we have been working on is, for example, quantum lattice-Boltzmann for acoustics, quantum lattice-Boltzmann for elastodynamics, quantum lattice-Boltzmann for shallow water equations, and so forth. And this kind of multiphysics tool that we are now building here is actually our first quantum product proof of concept that we hope to have out by early next year. So this is what we've been working on lately. Now, during the next couple of years, we hope to really integrate this proof of concept product that we're now doing as an integral part of the Quanscient AllSolve tool that we already have in use for our customers. And looking at the data and looking at the scaling of our algorithms, as well as looking at how the quantum computers are developing right now, we do expect to see kind of the first benefits of quantum computing in this field already within a couple of years. So we really look to see kind of the first quantum advantages coming not in too distant future. That being said, to really have like these universal benefits of solving Navier-Stokes for 3D airplanes in any arbitrary geometries and so on, that will most likely in the end require some sort of fault tolerance and error-corrected quantum computers. So that's still to be determined when that will happen. But the time from the first benefits, which I believe will happen already in a couple of years from now, 2 years from now, and then the time of full fault tolerance, that will be the interesting time, because we will start to see some benefits and we will be seeing more and more benefits going towards the fault tolerant era. So it's not kind of a clear-cut, discrete thing that, okay, now we have all the benefits, but rather these are incremental advantages or advances that we will be seeing. All right. That is already bringing me towards the end of my talk. So the key takeaways here are that, okay, Quanscient, we already have this tool called Quanscient Allsolve. It's fast, accurate, and scalable multiphysics simulations on the cloud. So if you are looking at multiphysics simulations in your work, it's something to check out maybe. But at the same time, from the very beginning, we have been developing these quantum native algorithms for multiphysics simulations. And we are really gearing up for quantum advantage with this, and we are more than willing to collaborate with talented individuals and organizations. So please be in touch. And that brings me to the end of my talk, and I'm happy to take any questions if there are any. Thank you so much.
Hello?
Hello, I can hear you.
Please, okay. Thank you very much for today's presentation. I would like to know if running simulations on your platform, please, is that what you were saying? You can run simulations on your platform. Okay.
Yes, yes.
Okay, please, is that free or we need to subscribe or something?
Yeah. So it's not free. So yeah, it's a software tool that you have to buy a license for. But that being said, we have if you are, for example, an academic, we have quite sizable discounts for academics. So for industry users, there's a different pricing, and for academic users, there's a different pricing.
Thank you very much.
And by the way, if you'd like to try out the quantum lattice Boltzmann algorithms in practice, you can actually go to the QR code, try our quantum demo, or just go to the link, and you can request access to the quantum demo, and you can try out these lattice Boltzmann method algorithms in practice from your laptop. Or if you're interested in buying the software itself, then you can of course book a demo meeting from us, but I'm not here to sell the software per se. Any other questions at this point?
Hello, sir.
Hello.
Thank you for your presentation. I want to ask if you offer internship position at Quanscient, and if yes, is it for everyone so that I can try apply?
So yeah, so the answer is yes and yes, but so currently there are no internship positions open, but if you follow us on our webpage, on the careers page, as well as on LinkedIn, that's where we will be announcing any jobs and internship positions. And whenever there is an internship position open, everybody is, of course, like more than encouraged to apply. So please do apply, and please do follow us to see any open positions. But unfortunately, right now there are no internship positions open. But that is likely to change in the near future.
Okay, thank you.
If there's no further questions, I thank you again for your attention. It's been an honor and pleasure to give you this talk, and hope to see you again in the future. Okay, thank you.
Hello, Doctor. I think there may be some questions.
Oh, okay. If there's still more questions, I'm more than happy to
I don't
answer.
know whether
Yeah.
this is the best time to ask. There's a lot of presentation with respect to the platform. If you have any particular question in terms of how.
Yeah, and don't hesitate to also
Proceed with your question.
contact me on email or LinkedIn or wherever after the presentation as well, if there are some questions that pop into your head after the presentation. Okay, there's
Okay.
one question. There's a question on the chat, I guess. So how do
Yes.
error
Comment.
correction
Yeah.
how do error correction challenges affect the deployment of quantum native multiphysics simulations on real devices? As I mentioned, kind of now in the NISQ era, while we still don't really have full-blown error correction, we rather just have error suppression techniques and error mitigation techniques. We can already do these proofs of concept, but this will not yet be, at the level where we can kind of solve bigger problems than would be possible on a classical computer. So we won't be getting quantum advantage quite yet. But as we get better and better error correction techniques and error suppression techniques as well, and as we get better and better devices and larger devices, we will start to see already in this NISQ era some first advantages. But to really get kind of a full-blown quantum multiphysics simulations product that you can just, throw any arbitrary geometry in and get the solution out, this will most likely require fully error-corrected quantum computers. And so it's still, some say 5 years, some say 15 years away, but we don't really know. But yes, it will require error correction in the end. But as said, already with NISQ devices and error suppression and error mitigation techniques, we will see the first quantum advantages happening in a couple of years.
So thank you very much. I think I was in your presentation for some time, and I saw the simulation. Maybe I don't know whether you can throw some more light to the participants concerning the numerical techniques in terms of whether you're dealing with a finite element, the mesh, or which techniques you use.
So you were asking me which techniques? Is that?
Yeah.
Okay.
In dealing with the mesh, the numerical techniques.
Okay. So yeah. Well, the Quanscient all-solve platform currently is that's fully based on finite element method. So that's the numerical technique there. And as I said, we use these domain decomposition methods to distribute the computation and parallelize the computation very efficiently. But that's finite element method based stuff. Now the quantum algorithms that we're developing, as I said, the numerical techniques are completely different because we have to kind of rethink the whole process. So we are using these quantum native, so lattice-Boltzmann method and lattice-gas automata especially. But yeah, classically we use finite element method. On the quantum side, lattice-Boltzmann method, lattice-gas automata.
Okay, that's fine. So with the simulation, that is what you were referring to the software, or there's some packages that you have to combine to any existing software that's available, like console or any other.
Yeah, so we have our own completely. We've written our own algorithms and we have our own user interface and everything. So that it's a full package that we offer. So you just log in on your laptop and you have a full-blown graphical user interface and scripting interface on your hands. You just don't need the hardware. You have the cloud hardware at your fingertips. So you can easily say use 100 CPUs on the cloud for your simulation, but you only need your own laptop. But in terms of physics capabilities, we have pretty much the same as COMSOL multiphysics, for example. So you can kind of compare it quite well to COMSOL, except that we have this cloud and also in the future this quantum capability with it.
Okay, great. I think you also mentioned some application in having to do with the equation that you are looking at. Is it all equations that are compatible with the numerical techniques that you are looking at, or specifically the few applications that you mentioned?
Yeah. So again, if we're talking about the quantum side of things, so yeah, we've developed quantum lattice-based algorithms for computational fluid dynamics type of simulations, as well as acoustics type of simulations currently. Those are kind of what we have right now. But as I mentioned, the lattice-Boltzmann method is at its heart, it's a solution method for partial differential equations. So it can be extended to also say computational electromagnetics or things like this. But then on the classical side of things, so yeah, basically the physics that is supported is kind of the imagination is the limit, because you can really write your own weak formulations for the finite element method in our software. So in that sense, you can really, whatever you can do with finite element method, you can basically do with Quanscient also.
Yeah, in fact, that's my next question, to find out whether the software package, it's possible you can be able to make adjustment and not having to be like a black box, some kind of just input and then output.
Yes, that's a great question. So how that works is that at any point you can move to the scripting mode where you can actually write, really your own weak formulations and kind of automatize anything you want and so on, and customize anything you want. But also, like a lot of these features are also in the graphical user interface. And actually, what's really nice is that whenever you click stuff on the user interface, that will always automatically generate your script. So at any point, if you want to add, for example, something that's not available in the graphical user interface, you can just move to the scripting interface, but you already have what you've done in the graphical user interface as a script available for you. So then you can just add, for example, another problem that's coupled to this problem. You just write the weak formulation of that particular physics problem, and it's all in Python, so it's relatively easy to use.
Well, I'm asking the questions for the students so they can ask questions, but then it looks like they are not asking any questions so far. So, I mean, working on this for a long time now, what are the challenges do you think that are there if any of the students are willing to do some work with you? What are the open avenues that they can decide to venture into?
Sorry, so the question was that, what are the challenges for the students and what should they be studying, and is that the question?
Yeah. So in working in this field, what do you think? I think since you mentioned earlier, it's something new that has come and you have been trying to do for a couple of years now. If any student is attracted to it and want to venture into this field, what are the open opportunities and challenges that they can try to also start working on?
Right. So I would say that the most important thing when kind of wanting to enter this field is to really first get the fundamental mathematics and fundamental physics really well. So you really need to understand the fundamentals and build the fundamental understanding, because that can then always be applied to many different fields. But in particular in this field, you really need kind of a very thorough fundamental understanding, I think. So really studying the maths and the physics is the really the key thing, I think. And when that's kind of on a good enough level, then it starts to make sense to really kind of start looking into, for example, how to program quantum computers. So there are really good resources by IBM, for example, in Qiskit. So the Qiskit textbook is a really good first thing to look at. That's an open source thing. So and it has really good exercises and so on. So that's for example a very good one. But yeah, really first getting the fundamentals right, and then slowly also starting to do the programming and the practical work. Of course, these must be done in parallel. But what I'm saying is that the fundamentals need to be really well understood.
Great, thank you. Please, any questions? Any question? I think I've opened a lot of avenues for you to ask questions. Do you have any questions to ask him?
Okay, I think I also have a question.
Sure.
About the scaling, the private subscription for the scaling part. So how do you monitor how much resources are used, and how do you price if I get a private?
Yeah. Okay. So yeah. So how it works is that there are different subscription plans that are based on the size of the cluster that you have available for you in the cloud.
Okay.
So if you have 64 CPUs available, that gives you some price. If you have 128 CPUs available, then you get some price. And then, of course, there's a certain limit of CPU hours related to that. But then if you run out of your quota for CPU hours, those can be always topped off at a relatively cheap price. But really the basis is the size of the cluster available to you on the cloud.
Okay, thank you.
And then the quantum part will be priced somehow differently, obviously, in the future, but that's another story.
Okay. Let me put it this way. I'm currently interested in working on something which has to do with carbon capture and storage. Fine. When you were mentioning some of the things, I've not seen anything in that regard, but I would like to know if your platform is also will be feasible to use for maybe optimizing some of the or using some of your optimization techniques to work on this kind of carbon capture storage project. I don't know if my question is clear.
Sure. So okay, so that's not something that's kind of in the focus area of we don't have customers in that area, for example, right now. However, of course, as long as you are dealing with solving partial differential equations, then our tool is good for that. But if you don't have if you don't have partial differential equations that you're solving, then you might be better off with some other tool.
Okay, thank you very much.
Thank you.
Okay. If there are no further questions, then we will have to bring today's talk to an end. And Lahtinen, thank you so much for honoring the invitation. I think we'll continue to talk. I have an email to send to the other lady from yours to continue the discussion from there.
Okay, thank you very much for inviting me to give this talk. So I will have to go now, but thanks again, and this was a very much a pleasure for me to do this. Thank you.
Thank you so much.
Bye bye.
Bye bye.